welcome to lecture 5. Last class we started looking at continuous time sinusoids and discrete time sinusoids, and we saw the two main differences. The two main differences are, as you keep on increasing the frequency, unlike in the continuous time case, in the discrete time case, the rapidity of the oscillations reaches a maximum and then the signal starts to slow down. The other important difference is not all frequencies give rise to sequences that are periodic. So, the discrete time sinusoid e to the j omega naught n. So, this, if it is periodic, then if and only if omega naught by 2 pi equals k by n, and then we also saw that you need to restrict yourself only in the range 0 up to n minus 1. So, k is actually k mod n. Any value of k that is outside this gives rise to a sinusoid whose k value falls within this range. So, just to recap some of the consequences that I had mentioned because of this towards the end of the last class. If you consider e to the j k omega naught t, as you let k vary in this interval, you get countably infinite number of sinusoids that are harmonic in the continuous time case. Whereas in the discrete time case, if you had e to the j 2 pi by n times k times little n, k takes on the values 0, 1 up to cap n minus 1. Therefore, k here belongs to the set zero to 1. So, this is a finite set. So, in the discrete time case, the number of harmonically related sinusoids is a finite set, whereas in the continuous time case, the set of harmonically related sinusoids is countably infinite. So, this is one consequence that follows. The other consequence is, if you had e to the j omega naught n, omega naught belongs to the interval 0 to 2 pi, or equivalently minus pi to pi. As omega naught varies from 0 to 2 pi continuously, you get an uncountably infinite number of sinusoids that are generated. Of these, only cap n of them are periodic, and those cap n set of sinusoids that are periodic have to satisfy omega naught by 2 pi equals k by cap n, and in those instances the periodicity is cap n. So, even though you have uncountably infinite number of sinusoids as you vary omega naught from 0 to 2 pi, only n of them are periodic. On the other hand, if you had e to the j omega naught t, in this case omega naught can take on values in the interval minus infinity to plus infinity. For every single value of omega naught, the continuous time sinusoid is periodic. For every single value of omega naught, as omega naught goes from minus infinity to plus infinity, every single sinusoid is periodic with period t equals 2 pi by cap omega naught. So, this is always periodic, period is 2 pi by mod omega naught. So, these are the two main differences that you see between continuous time and discrete time. The set of harmonically related sinusoid is finite, whereas in the continuous time case, the set of harmonically related sinusoids is infinite. And in the continuous time case, it's always periodic, whereas in the discrete time, it is periodic only if this condition is satisfied. Now, let us look at another aspect of sinusoids, again to reinforce some of the ideas that you may have already learnt from signals and systems. So, let us consider xk of n of the form e to the j 2 pi by cap n times k times little n. So, these are clearly harmonically related sinusoids, and k of course goes 0 to n minus 1. And these are periodic, and there are n such sinusoids here. So, as k varies, you get distinct sinusoids. For each value of k, you get distinct sinusoids. And distinct is kind of a term that we understand, but we need to make it precise mathematically. So, when I say as k varies, goes from 0, 1, 2 up to n minus 1, for each value of k you get a distinct sinusoid. If you want to make it precise, what would be your way of making it mathematically precise? We know loosely what it means to say that these are distinct. We kind of have a picture, but the frequencies are harmonic, okay? All right, but then remember, here we are trying to make precise the notion that these two sinusoids are distinct. I mean, is there an equation that you can put down to capture this? Okay, orthogonality is a good guess. So, if two sinusoids are not orthogonal, then does it mean they are not distinct? I mean, orthogonality is a very good guess. I mean, say this definition and then see whether you can pin it down to an equation. The notion that I am after is I want two sinusoids to be independent. And the reason why I was a little hesitant about orthogonality is when it comes to vectors, there are vectors that can be independent but not orthogonal. So, here drawing upon your knowledge of two vectors being independent, if you want to talk about two signals being independent, how would you quantify that notion? So, two signals or sequences, in this case two signals are independent if a1 x1 of n plus a2 x2 of n equal to 0 implies a1 equal to a2 equal to 0. So, this is the notion of independence of signals. Now let us consider the general case. Here we have considered the case where we have xk of n e to the j 2 pi k n by n. So if x1 is e to the j omega 1 n and x2 of n is e to the j omega 2 of n, and we are given that omega 1 is not equal to omega 2. Then you can actually verify that a1 e to the j omega 1 n plus a2 e to the j omega 2 n equal to 0 will imply a1 equal to a2 equal to 0. Alright. So if you have two frequencies omega 1 and omega 2, these are independent. So this is an easy thing to verify. What's the intuition behind this? You can also gather an intuition from this equation. If two signals are dependent, then one can be expressed as a constant times the other. So this is what dependence means. And this constant in general can be complex. Therefore, it's easy to see once you have this intuition associated with dependent signals. If you have two distinct frequencies, no way can you take one sinusoid multiplied by a complex constant and get the other signal which is a different frequency. So it's very clear that if two frequencies are different, they cannot be a scalar times each other. All right. Now, in particular, once you have this definition in place, e to the j omega naught n and e to the minus j omega naught n. That is, if the two frequencies are omega naught and minus omega naught, then these two signals are dependent or independent. Are these two signals dependent or independent? Independent. Some of you think it's dependent. Okay, why is omega not equal to pi a special case? Yeah, that's a very good observation. So, if you have, this is a special case in which omega 1 is omega naught and omega 2 is minus omega naught, right? So, this is true for all omega 1 not equal to omega 2, all right, where omega 1 is omega naught here and omega 2 is minus omega naught. So, they are independent, okay. And as was observed correctly, the only exception to this is when omega naught is either 0 or pi, right. If omega naught is 0, then e to the j omega naught and e to the minus j omega naught are the same. When omega naught is pi, e to the j pi n and e to the minus j pi n are exactly the same signal, okay. Therefore, exception to this is omega naught being either 0 or pi. So, this is the general case. So, this also applies to the case when the signal is harmonic. So hence xk of n, yeah, go ahead. Okay. Okay, let us examine omega naught equals pi by 2. So I then saying e to the j pi by 2 n and e to the minus j pi by 2 n are the same. One can be expressed as no. Okay. Okay. So when you're taking two, when you're considering real valued signals, we'll come to real valued signals after this. Okay. But when you're talking about the linear combinations, you're considering the special case of e to the j theta plus e to the minus j theta of that form. Correct? Am I understanding you right? Yeah. So that's the real valued case will come now. So xk of n equal to the e to the j 2 pi k by cap n times little n, as k goes from 0, 1 up to n minus 1. So you have cap n independent signals. So we have xk of n plus cap n equals xk of n, and there are n independent signals that are harmonically related. Now let us come to the real valued case. Note that e to the j omega naught n and e to the minus j omega naught n are independent. Applying that to this specific case, if you put say k equal to 1, you get e to the j 2 pi by cap n times little n. So this is one signal, and if you put k equal to n minus 1, you have e to the j 2 pi by cap n times n minus 1 times little n. So here is an example within this set of two complex exponentials that are independent. And remember, k equal to n minus 1 is also the same as k equal to minus 1. Therefore, this is the same as e to the minus j 2 pi by cap n times little n. So here are two specific examples of this set in which the two sinusoids complex exponentials are independent. So we will use the term sinusoids, complex exponentials interchangeably. Even when the signal is a cosine, we will refer to that as a sinusoid. Now coming to the real valued case, suppose you have cosine omega naught n, and if you consider cosine minus omega naught n. Remember, in the complex case, e to the j omega naught n and e to the minus j omega naught n are independent of each other, which means you cannot take e to the j omega naught n, multiply by a complex constant and hope to get e to the minus j omega naught n. These are two completely independent signals. For the real valued case, what about cosine omega naught n and cosine minus omega naught n? They are exactly the same signal, therefore this is dependent. And the constant associated with them is unity. You can go from one to the other by multiplying by 1. Sin omega naught n and sin minus omega naught n, again they are dependent, and the constant that you need to use to go from one to the other is minus 1. All right. Therefore, these are dependent signals. So one fallout of this is that this implies you need to restrict yourself as far as omega naught is concerned only in the interval What's the range of omega naught you need to consider when you consider real valued sinusoids, both cosine and sine? 0 to pi. 0 to pi, both points included. Because any frequency that's in the interval pi to 2 pi can always be generated as a frequency in the interval 0 to pi. And as an illustration of this, suppose you have x of n to be cos 1.6 pi n plus theta. So here is an omega naught that is greater than pi. So this can be written as cos, so here, so this is omega naught which is greater than pi. So this can be written as cos 1.6 pi n minus 2 pi n plus theta, nothing has changed. So this in turn is cos minus 0.4 pi n plus theta. And since cos of minus theta is cos theta, I can also write this as cos 0.4 pi n minus theta. And now if I focus on this, if I call this as omega 1, now this is less than pi. This illustrates the fact that any real valued sinusoid whose frequency is greater than pi, or in particular it's between pi and 2 pi, can always be transformed to another sinusoid whose frequency is between 0 to pi. That's all. That's the main point of this. Okay. Whereas you cannot do this in the case of a complex sinusoid. All right. In the case of complex sinusoid, you need to consider omega naught in the range 0 to 2 pi. All right. And in terms of harmonic sinusoids, right? Suppose if you consider cos 2 pi k by n and sine 2 pi k by n. So these are real valued periodic sinusoids. So what is the range of k you need to consider? What is the range of k you need to consider for these two specific real valued sinusoids? Okay, so those are correct answers. So you need to consider the value of k between 0, 1 up to n by 2, where n is even, or n minus 1 by 2 when n is odd. Because any value of k that exceeds this can always be mapped to an index k that is between 0 to n by 2 or n minus 1 by 2. All right. Now, recall this particular thing, that is so we saw this, right? The set of complex sinusoids that are harmonically related, e to the j 2 pi k by n times little n, and k went from 0 to n minus 1. And there are n independent sinusoids in this set. For each value of k, you will get a sinusoid that is independent of any other value of k. So totally n independent sinusoids are there. Now let us come and look at this. Now let me look at this particular set. So k goes only from 0 to n by 2 or n minus 1 by 2. How many independent sinusoids will be there when you look at cosine and sine? So this is an exercise that I want you to try out later. So, how many independent signals are there in this set? So, all you need to do is you need to consider the case n odd and n even separately, and whether it is n even or n odd, you have to convince yourself the total number of independent signals in this set, when you consider both cosine and sine together, the total number is indeed still only n. Alright, even in this case the number of independent signals will only be n. Okay. But for that you have to enumerate all the signals considering n odd and n even separately. So, this is a simple exercise, but make sure you do it and you are comfortable with the answer that you get. You have to convince yourself that indeed even in this set also there are only n independent signals. So, again continue on this independence, just to wrap up with a couple of more points. If you have cosine omega 1 n and cosine omega 2 n, omega 1 not equal to omega 2, again these two signals will be independent or dependent? It will be independent. Therefore, C1 cos omega 1 n plus C2 cos omega 2 n, when omega 1 is not equal to omega 2, will imply C1 equal to C2 equal to 0. Similarly, for sin omega 1 n and sin omega 2 n, these two are independent when omega 1 is not equal to omega 2. And finally, suppose the frequency is the same. I have cos omega naught n and I also have sin omega naught n. Are these independent or dependent? Again, this should be very easy. All you need to ask at an intuitive level is, can I take cosine multiplied by a constant which can take on even complex values? Can I take cosine multiplied by some constant and get sine? Is that possible? No. Therefore, for the same frequency, cosine omega naught n and sin omega naught n are independent. Therefore, C1 cos omega naught n plus C2 sin omega naught n equal to 0 will imply C1 equal to C2 equal to 0. So, this kind of ties up all the things related to discrete time sinusoids.